Hi guys, in this lecture we will try to understand the concepts of electric field intensity and Gauss law in electrostatics. So before we try to understand the electric field intensity, it is very important for us to understand the basic law in electrostatics, that is the Coulomb's law of force. So everybody would have been familiar with the definitions of the Coulomb's law of force. So what it says, when there are two charged particles, say q1 and q2, separated by a distance of r in a medium, there exists a force of attraction or a force of repulsion. That basically depends on the polarity of these two charges. So we'll see the direction part later. So when it comes to the magnitude part, so the first thing is here. The definition says the magnitude of the force is directly proportional to the product of the charges, and it is inversely proportional to the square of the distance between the charges. Now, when I combinedly write, so the force is proportional to q1 q2 by r square. So when I remove the proportionality constant, I can introduce a new constant, let us say k, q1 q2 by r square. We all studied the proportionality constant k, so I can define the value of k itself is equal to 1 by 4 pi epsilon. So the constant epsilon is basically said to be the permittivity of that medium. Suppose if it is for free space, the permittivity will be exactly equals to 8.854 into 10 power minus 12 farads per meter. So we'll come across this particular term in the later discussion part. So as per the definition is concerned, the force is basically a vector quantity. So the magnitude part, I can say that k will be replaced by 1 by 4 pi epsilon q1 q2 by r square. So this represents the magnitude of the force between the two charges. In the next part, we will see what is the direction of the force if both are of positive charges, or if one is positive or one is negative. So that we will discuss in the next part. And here everybody has to notice a very important point. The first thing is, so this is what the definition for the Coulomb's law force we have studied in our textbooks. But in the reality, what actually happens, suppose if this mass of the charged particle, let us say both q1 and q2 are having a mass of m. So if the mass of the charged particle is much higher than the separation between the charges, now what will happen in this case? Since the mass is very high, so always there will be a ground plane right here. So when this mass is quite high, so there exists a gravitational force, you can say, which is nothing but mass into acceleration, which is quite dominant. In other words, when the mass of the charged particle is too high, the gravitational force is going to be the more dominant force compared to the Coulomb's law of force. So in other words, I can say that the Coulomb's law of force is significant when the mass is quite negligible compared to that of the separation between the charges. I hope the point is clear. So I can say that the Coulomb's law of force is significant provided the mass will be much lesser than the separation between the charges. You have to keep it in mind. So the magnitude of the force is clear. Now let us try to move on to the direction. So here I have clearly explained here. So let us consider the first scenario. One charge is positive and the other charge is negative. So those are said to be the unlike charges. That means both the charges are having a different polarity. Now in this case, what will happen? The tendency of the charged particles will be, since both are unlike charges, this charge is trying to move towards the minus q charge, and the minus q charge will try to move towards the plus q charge. So whenever the charges are unlike, they try to attract each other. Now consider the like charges. So this is also the positive charge, or this is also the positive charge. It may not be both positive, it can be both negative as well. So this may be minus q and this may be minus q. So in this case, what will happen? Since both the polarity are same, this plus q charge is trying to move away from the other charge like this. And similarly, this charge is also trying to move away from the charge because of the same polarity. So when the charges are of same polarity, or you can say the like charges, they try to repel each other. So the summary is the unlike charges are attract each other and the like charges are said to be repel each other. Now, the very important concept we have to discuss now, that is nothing but the electric field intensity. So basically, what is the definition of electric field intensity? So when you see the definition, electric field intensity is also a force experienced by a unit positive charge. So let me give an example for that. So consider there is a positive charge located in a certain medium. So in our elementary physics, we have studied that. So every charged particle will create some kind of field. So there will be a field which is existing nearby this region. So whenever there is any charged particle, the field will be lies away from the charge like this. This is what we have studied in our elementary physics. So but what actually electric field intensity defines now? Quantitatively, how much field is existing at a particular point. So the magnitude of the field at a particular point is basically said to be the electric field intensity. Now the definition is clear. It is the force experienced by a unit positive charge. So let us say this is a particular point where I have to find out the magnitude of the electric field intensity. So what actually says the definition? It is the force experienced by a unit positive charge. So let us say this is your charge and this is your observer and the distance is r. Now as per the definition, wherever you want to find the electric field intensity, something like this, I have to place a unit positive charge there. Now what the definition says? The magnitude of the electric field intensity is same as the magnitude of the Coulomb's law of force. So one is of charge q and the other one is of 1 coulomb. So what is the Coulomb's law says? Q1 is q itself and q2 is plus 1 coulomb divided by 4 pi epsilon, and the spacing between this q and the 1 coulomb charge is exactly r square. So I can say what is the value finally? The electric field intensity due to a point charge at a distance of r is given as q by 4 pi epsilon r square. This is basically only the magnitude part. And the electric field intensity is in turn, it's a vector quantity, right? So what will be the units of this electric field intensity now? The next thing. So electric field intensity is nothing but the force per unit positive charge. So I can say the units will be Newton per Coulomb, or you can say volt per meter. So the point is very simple. Wherever you want to find the electric field intensity, imagine that there exists a unit positive charge. You place the point at that position. Then apply the Coulomb's law of force to find out the magnitude of the electric field intensity. So in other words, the electric field intensity quantitatively measures how much field is existing at a particular point of interest. So that is basically said to be the electric field intensity. Now, so the magnitude part is clear, and the very important thing what we need to understand was the direction. So let us consider the direction part. So in the first case, I have considered the charge is positive. So this is my source where the charge is located, and this is my position where the observer is located. So the source corresponding to the point where the charge is located, original charge is located, and the observer is the point where you are finding the electric field intensity. As per the definition is concerned, at the observer, a unit positive charge has to be placed, right? So I have placed a unit positive charge at the observer location. Now consider what happened when the source is positive. We have seen in the Coulomb's law of force, this is also positive and this is also positive. So what will happen? This 1 coulomb charge is trying to move away from the plus q coulomb charge because of the same polarity. So when the source is positive, the observer tries to move away from the charge. So the direction of electric field intensity will be away from the source. In other words, I can say when the charge is positive, the direction of electric field intensity from source to observer. In other words, observer will be moving away from the source. So the electric field intensity is lies from source to observer. I hope the point is clear. And consider the next case when the charge is negative. What will happen when the charge is negative? You know that at the observer already a unit positive charge is placed. So the observer is of positive polarity and the source is of negative polarity. So what will happen now? The observer tries to move towards the source. So what will happen? There exists attraction between these two charges. So whenever the charge is negative, the observer is trying to move towards the source. In other words, the electric field intensity is from observer to source. So when the charge is negative, the direction of electric field intensity will be towards source. Or in other words, you can see here it is from observer to source. So when I summarize here, when the charge is positive, the direction of electric field intensity is away from the source, radially away from the source. When the charge is negative, the electric field intensity will be radially towards the source. This is valid irrespective of whether it is a point charge or there are different types of the charges are existing, right? Line charge, surface charge, etc. So the same shortcut we are going to follow even whether whatever the type of charge it is, whether it is a line charge or surface charge, it doesn't matter. When the charge is of positive polarity, the electric field intensity will be radially away from the source. When the charge is negative, the electric field intensity will be radially towards the source. So from the understanding of the electric field intensity, we will come across one more parameter that is called the electric flux density. So what is basically the electric flux density means? So you can see the definition. It is defined as the electric flux per unit area. So here you have to notice a particular point that the electric flux in electromagnetics is also said to be the charge itself. So we'll come across this later. So as of now you can remember that the electric flux is basically same as the charge only. So let us try to understand the parameter electric flux density with some example. So consider there exists a point charge of magnitude q coulombs located in a certain medium. You know that the flux lines are omnidirectional like this. And for an example, I have considered a small surface here to capture the flux generated from this source. Now when you consider this particular surface, only a small part that I have represented in the blue color is only passing through this surface, isn't it? Now in this case, the flux density is basically defined as, the flux density is defined with a symbol D, which also stands for displacement flux density, is defined as the electric flux passing through this particular surface divided by the area of this surface. So the electric flux density is same as how much flux is passing through this surface divided by the area of this surface gives the magnitude of the electric flux density. Now what will be the units of this now? The units of the electric flux density is same as the electric flux per area, right? So I said the flux is indirectly related to the charge. So the units will be in the order of Coulomb per meter square. And there is one more thing, the direction, right? So the direction of the electric flux density and the electric field intensity both are same, because we already studied in our elementary physics that the displacement flux density is basically called epsilon times E, right? So where epsilon is called the permittivity of the medium. So let us try to understand what is actually the permittivity of the medium represents. So the permittivity represents the capability of that medium to allow the electric field into that. For example, if I say that a particular medium is having high permittivity, which means that medium can easily allow the electric field through that. So that it is the capability of the medium to withstand or to allow the electric field into that medium. So that is said to be the permittivity. It is a basic, very important property of any medium. And the permittivity is mathematically defined as, you know, that epsilon is said to be epsilon naught times epsilon r, and epsilon naught is said to be the free space permittivity, you know, the value of the free space permittivity we already studied, 8.854 into 10 power minus 12 farads per meter. So in other words, the same value I can represent in this term, 1 by 36 pi 10 power minus 9 farads per meter, and epsilon r is said to be the relative permittivity of that medium. So what actually relative permittivity defines? It's basically a constant. If it is for free space, the relative permittivity will be 1. If you are going for other dielectric medium, basically the relative permittivity will be quite more than 1. So based on one medium to the other medium, the relative permittivity will be changes. So in this slide, what we have understood is the concepts of the electric flux density, and the electric flux density is defined as the electric flux per area. So the definition, if you consider, if you take any surface, the amount of the flux passing through that surface divided by the area of that surface gives the definition of electric flux density. And the electric flux density direction is same as the electric field intensity direction. Now let us move on to the Gauss law. So we have understood the concepts of the electric flux density, right? So what is the Gauss law says? The net electric flux leaving any closed surface is exactly equals to the total charge enclosed in it. So before understanding this point, you have to remember two things. The first thing is electric flux is same as the charge. You have to keep it in mind, right? Now consider an example where there is a positive charge or negative charge. Let us say some charge is located in this particular medium, and this charge is enclosed by a closed surface like this. So what is this closed surface represents? Whatever the flux generated from the source will be captured by that surface. So consider the same scenario. Look at the definition of electric flux density, right? So the electric flux density is nothing but the electric flux per area. In other words, I can say the electric flux, let us define it as some psi is equals to mathematically double integral d dot ds. So it is nothing but the flux density multiplied by area. So in a mathematical form, I can write psi is equal to double integral d dot ds. This gives the electric flux passing through a surface, something having an area of ds, right? Now in this case, what happened? The surface is closed, isn't it? When the surface is closed, how much flux is captured by this surface? So mathematically, what it says, when the surface is closed, what will happen? The net electric flux, I can define it as, it is same as double integral d dot ds. Now this time the surface is closed. This magnitude is equals to how much? So try to understand the basic concept. The electric flux is having the same unit of the charge, right? See, the flux density will be Coulomb per meter square and the area will be meter square. So the electric flux is basically same as the charge itself. Now consider this example. So there is a charge and this charge is enclosed by the closed surface. So what will be the total amount of the flux leaving this closed surface? So since you have taken a closed surface, you are able to capture all the total flux lines which are generated from the source, isn't it? Is there any flux which is missing out? Definitely no. So since you have taken a closed surface, the net electric flux leaving this closed surface is exactly equal to the sum of the total flux generated from the charge itself. See here, if you calculate the sum of all these flux lines are originated because of this charge itself. So when I can add the total sum of all these flux lines, that is same as exactly equal to Q. So what I try to say, when you take in any closed surface, the flux leaving this closed surface is exactly equal to the sum of all the flux lines, which is same as the charge q itself. That is what the Gauss Law says. So this is a very important thing. Whenever the surface is closed, the double integral d dot ds is exactly equal to the charge enclosed in it. So based upon the Gauss law, there are so many problems which have been simplified very easily. Suppose if you want to calculate the electric field intensity due to a particular type of charge, this Gauss law is very helpful. In my opinion, actually, I'd say I like the way how the Gauss has been given this expression. In my opinion, Gauss is a famous mathematician cum physician. So what I meant to say was, he don't want to talk too much, and this his equation will tell a lot of information in that. So that is the powerful thing about this Gauss law. So once the Gauss law has been evolved, there are so many complex charge distributions, and you can easily evaluate what is electric field intensity due to that different type of complex charge distribution. So that is what the beauty of the Gauss law is. Now we try to verify what the Gauss law and the Coulomb's law is. It both are related or it's quite different. So try to verify the Gauss law and in this particular slide. So for that also, you consider there is a charge located in a particular medium, and this charge is enclosed by a Gaussian surface, basically I can call. So this is how you are calculating the electric field intensity if any charge is known. So what I have considered? I have considered a point charge here. This is enclosed by a closed surface, which is also called as a Gaussian surface. I want to find out the electric field intensity due to this point charge at a distance of r. We already seen using the Coulomb's law, right? So what the Coulomb's law says, whenever there is any point charge, the magnitude of the electric field intensity is equal to q by 4 pi epsilon r square, right? The same thing let us try to verify with the Gauss law. So what the Gauss law says, using Gauss law, the net flux leaving any closed surface, in this case, is equal to the charge enclosed q itself. So see here, you have considered a Gaussian surface having a radius of r. So when you do the mathematical analysis, what will happen? The flux density, take it out. What is the surface area of this closed surface? 4 pi r square is equal to q itself. So the flux density is equal to q by 4 pi r square, which is same as epsilon times E. We have studied D is equal to epsilon E. I'm sorry, once again I will write double integral d dot ds is equals to q enclosed, and d into 4 pi r square is equals to q itself, and the flux density is equal to q by 4 pi r square, which is same as epsilon times E. So the electric field intensity is equal to q by 4 pi epsilon r square. This is what the same definition you got with the Gauss law also, right? Coulomb's law also. So the Coulomb's law of force also said the same thing, electric field intensity, and the Gauss law also has proven that with the same simplified mathematical equation, you are able to derive the electric field intensity. So both are verified. So I would like to conclude the session here. Thank you very much.